how to build a self-driving car in your garage. So this technology is already here, and it's already here for everybody to use. It's not in a lab setting. It's not something that you have to be in like a compound to use or whatever. It's here. This is 100% software problem. It's not a hardware problem. So the one big bottleneck to self-driving cars and robotics to some extent is that there is no good world simulator. So now you're in a different world, a world that you don't have training data for. Like all the data that Comma has are data of like decent driving, right? I mean, nobody like flew off a cliff. And this is the counterfactual world information that you do not have. Hi, I'm Vivek. So my talk today is how to build a self-driving car in your garage. It is a bit provocative, but you can actually do this. You can, if you have a supported car, get self-driving abilities on your car today. So I'll talk about like what the goal of this talk is and what would be a happy outcome for me at the end of this talk. But yeah, this is my talk. So just a little bit about me. I'm a co-founder of a company called minusx.ai. So we build data agents for data analysis, mainly Metabase. Previously, I was a research engineer at comma.ai. So a lot of my talk is from Comma, but yeah. So I worked there for over 3 years. And before that, I did my grad school at UC Berkeley, and then I did my undergrad in IIT Kharagpur. So these are my socials. I'll share the slides so you'll get the slides after the talk. Okay. So self-driving cars are already here. So how many of you have watched videos of self-driving cars? Okay, great. How many of you have seen one in real life? Okay, how many of you have sat in one? Okay, awesome, great. Yeah, so you guys are all, you all know what self-driving cars are, what the promise is, and what a world with self-driving cars would look like. So they're already here. So this was me in a Waymo, I think earlier this year. So you can see that it's just turning and just taking me wherever I want to go. This is, this is a Comma user who did 100 miles, I think, in like one video. And then this, you can see he's not touching his steering wheel. It's just, it's just going about. This is me and a friend of mine. We are in a tree farm. I don't know if you can see. You can see the roads. There are no roads. There's just like a brush path. It's a tree farm. It's a farm of Christmas trees, and me and him went to get a Christmas tree, and this is us just engaging OpenPilot, and then OpenPilot just drives. So this technology is already here, and it's already here for everybody to use. It's not in a lab setting. It's not something that you have to be in like a compound to use or whatever. It's here. Everybody can use it. Great. So I'm going to talk more specifically about OpenPilot. So how many of you here have heard of OpenPilot? Okay, awesome. How many of you have cloned OpenPilot on your computers and installed it? Okay, awesome. So this is the goal of my talk. At the end of this talk, if you understand the repo structure of OpenPilot, if you have the confidence and the interest to clone it, to install it, and to play around with it, and I have a problem, and if you can solve my problem, and if you're motivated to do it, that would be a great success of this talk. Just so I'm setting the expectation that I will get emails of every one of you, and I will ask 1 week later if you've done this. So yeah. So what is OpenPilot? So OpenPilot is an open source self-driving agent. You can go to GitHub right now, go to that link right now. You can use it, you can download it, and on your computer, you'll have an agent that potentially can drive a car. So let's understand what that is, what that entails, what are the different components and everything else. So OpenPilot supports all major car brands in the US. It's like they support more than like 300 different car models. So I think mostly all cars manufactured after 2016, I think, are supported. And the way to know if they have a page, you can just go and check. But cars that have LCAS, which is lane keep assist, and cruise control. If you have these two in your car, I mean, most probably OpenPilot can work on your car and can drive your car. So these are like the range of the cars. There's like a massive, feels like a missile when you sit in one, a Ram 500 and like a tiny Bolt. And it can, the same driving agent drives both cars. So I just want you to keep in mind that it's the driving agent and not something that is like specific to your car or like, it's not something hyper specific to any one particular car. It's a driving agent that sort of looks at the road and just knows how to drive and then just drives. And that screenshot right there is Consumer Reports, which is like a very popular like a testing agency, I guess, in the US. They did this a few years ago. They rated all ADAS systems, and then comma.ai, which was the version of hardware at that time, is like the top. It beats all the Tesla and Audi, whatever, all the other ADAS companies. So what all do you need to have a self-driving car?
Good question.
Yeah.
Why do you need the lane keep assist?
So the way I'll talk about the way that OpenPilot works is that, if you have lane keep assist and cruise control, that means the car has the APIs that can be automatically controlled. So what OpenPilot is doing with the hardware, which I'll talk about, is that it sort of sits in the middle, intercepts the messages, and then sends its own messages to control. And this is sufficient for you to drive your car. So most cars already have the sort of capability to do it. It's just that the software is not good enough.
Oh, I see. For left and right, you need lane keep assist.
Yeah, just for steering. Just for steering the car, like turning and everything else. Which is another thing that I want you to take away from this talk is that this is a 100% software problem. It's not a hardware problem. The hardware already exists, which is your car. And like some small hardware to like communicate with your car. It's a 100% AI software problem. It's we have the video. So if I show you a video of like a car, you will be able to drive it. Sitting here, you'll be able to if I give you a joystick, you'll be able to drive no problem. But like driving agents are not perfect yet, and it's a 100% software problem, which is something to keep in mind. So okay, so what do you need for a self-driving car? So you need a car. So a car after 2016, I guess. So you need a way to communicate with the car, and this is the hardware that Comma makes. So the version currently is Comma 3X. It's a version, it's like about $1,000. So this device, so what it does effectively is, there is another open source project called OpenDBC. So what it does is, so your car communicates internally through CAN messages. So these are the messaging protocol in your car. So OpenPilot communicates with the car through the same messaging protocol using OpenDBC is a way for to convert your car messages, CAN messages, into things that we understand, like battery level and speed and acceleration and whatever else. So this is a project that, again, an open source project. For almost all cars in the world, you have conversions now. So what this means is, even if you don't want to self-drive your car, you can install this. You can get logs. There are a bunch of hardware that gives you CAN logs. You can run it through the profiler, and you can understand what messages are being sent, all around your car, and you can control stuff. You can some cars have blind spot monitor, blinker lights. You can with a computer control your blinker lights. That's cool, right? That's super awesome. So this is. So Panda is another sort of open source project by Comma. So what Panda does is it sits between the self-driving software and the car, and then Panda is what gives the guarantees that the OpenPilot sort of has some guarantees that a car will never fight you. When let's say the car wants to turn left and you want to turn right, it will never fight you. And all of these things are implemented in Panda, which is another repo. So OpenDBC is something that you should talk. I've put links for everything. That is something that you can look at for all the conversions between all the internal car messages to instructions and information that we can understand. Okay, so you need this. Yeah.
So this device, you're connected somewhere.
Yeah. So you can connect this near your mirror. There is a camera port. You can just connect it right there. Yeah, so there is a harness. So the harness depends on the car. It depends on the brand usually. So you can buy the harness. So on the buying page, you can go to the buying page. You can like choose your car model. They send you what harness, and you can buy it, and then you can connect it. Yeah. So the way, I'll talk about. And then, so the third thing you need is AI. You know, if you know, this is like the magic ingredient that you need to drive your car. And the last thing you need is some good road trip music on Spotify. So if you have all these things, you'll have a self-driving car. So the sort of technical or another representation of this is this. So you have your car. You have CAN messages that come out of your car. So the comma device that is in the green gets these. The comma device is basically a device that you mount on your windshield, and you can connect it to your car. And then the comma device has some sensors. So it has front-facing camera. It has two front-facing cameras, one driver-facing camera. It has GPS, IMU, a bunch of other sensors. So I'll talk about why the driver-facing camera is also important. So and then, so the software is, again, it takes all the sensor data. It takes the CAN messages and everything else, and does a few things. So one is it sort of builds a model of where you are. So it's the localization piece, which is like, where you are in the world and what are your states. And then, we have the driving model, which is the AI, which sort of takes all of these things in, all the sensor information, all the sort of car information, all your states and everything else, and predicts what to do next. And the prediction of what to do next is sort of car agnostic. It just takes a bunch of information and predicts what to do next. And then that information goes back to the device, it's in the device, and then that information goes back to the car, converted to what specific instructions to implement on the car. So this is both technically what specific information to implement, and also there is the information to implement because of like differences in cars. So because OpenPilot supports all cars, right? The instruction of like I need to turn slightly right in the road is information that your model can provide. But then what does that mean? Like that should translate to literally how many degrees I have to move my steering wheel and how much pressure to put on the gas brake, right? And this is information, again, there are like components that convert the model instruction into this information of exactly how much gas brake, how much steering, and then goes back to the car and is implemented in the car, and then this whole loop goes on. So this is the basic architecture of like how OpenPilot works. These are again some GitHub links that you'll be able to get. So when you do all this, what do you get? So this is, I guess the contrast is not great. This is a world map. I asked a friend of mine today to give me a screenshot of, this is all the drives in the last month, I think. So you can see this US majority penetration is in the US, and you can see in Europe, and then you can see in other places of the world. There are some drivers in India, so you can, I don't know if you can see, it's like a tiny dot in India as well. So yeah, this is something that people anywhere in the world can just install and drive. Okay, so this is all we get, right? I'll take you through like a first-person view. Okay, so what is happening here is that this is a video, the car is driving, and then the light turned red, and the car automatically came to a stop.
What's happened?
Yeah, so that was OpenPilot in action. That was fully engaged OpenPilot doing that. I also wanted to show you a live demo.
So we're providing.
Oh. Let's see.
Oh.
Okay. Yeah, so this is when you guys install OpenPilot, which I'm sure all of you will do. These are some things you can do. So I'm just going to run.
Here's zoom in.
Yeah, so it's going to. Yeah, so this is basically replaying an entire route. So this is exactly like a drive, somebody's drive. And then we can see what happened in that drive. So if I just go forward a little bit. So you can see this person, he hit the lane change command. And then you can see automatically the car like change lanes. And this is fully engaged. And this is the car doing it.
Is it like a simulation?
No, this is an actual drive. So this is literally an actual drive that happened with someone. It's just all the logs, and I'm just replaying all the logs.
You're replaying
Yeah, I'm just replaying all the logs, but you can see the turn. This is like literally what happened when that person was driving. This was actually my commute to office in San Diego.
So you have.
Yeah, I mean, you can keep watching it. But this is something that when you install OpenPilot, this is something that you will be able to do. Okay, so what more can you do when you install OpenPilot? This, let's see. Okay, so this is the view that you get, when this is the device basically. So I'm running a simulated device right now. Let's see. So that is literally the software running in a simulated device, okay? And now I'm also running a simulation of a world. So this is, it's a world car simulation software called MetaDrive. It's also an open source project. Yeah, okay. So this is MetaDrive, and OpenPilot is running in MetaDrive, and it's not able to run. This is my problem. And at the end of this talk, if anybody is motivated to go ahead and fix it, you can fix it right now. You can go check what the issue is, try to run this. There are some errors that come out, and it's open source software. You can contribute, and then it will be upstreamed. It will be merged into OpenPilot. This is something you can do right now. So but the basic idea is it's a virtual world in which there are some roads that you can define in code, and then you can run OpenPilot live on this scenario, and it will run, and the model that will run is the exact same model that has been trained by human driving data. Like all the data that humans have driven, it's trained, the model is trained, and the same model will take this as the input, the MetaDrive world as the input, and will actually drive your car. So you can potentially devise all sorts of like crazy scenarios with like other cars zooming in and people running all over and whatever else, and you can like see how OpenPilot performs. And this is something that you can contribute to OpenPilot like right now, which that would be great. And if you can fix this problem, that would be awesome.
Has anyone tried to run OpenPilot on Need for Speed or similar game?
Yeah. People have run it on GTA, and people have run it on Mario Kart. Yeah, so these are all projects that are super accessible to everybody here. It's like, so you can just look at the MetaDrive part of how the bridge is happening, and you can just implement the exact same thing for whatever like simulator you want, which is a game or whatever else. Yeah, somebody did it for Mario Kart, somebody did it for like a truck simulator. Yeah, and you can do that. And the output of that, when you fix it, will look something like this. So this is the MetaDrive world. I guess this is pretty boring, but the car drives. But you can add whatever scenarios you want, and then you can test out. You can take your virtual car for a test drive. That is something that you can do. Okay.
Sorry.
Okay, so why is this a hard problem, right? So everything till now looks great. You can have, we have the device right now. We have all the communication figured out. Everything works great. We can control, we can give whatever commands we want, from our computer to the car, and the car should drive. But why is this still, why can't you today go out, get a cab in a self-driving car and go home? And the reason, there are two main reasons. The first one is that hardware is hard. And hardware is hard in, obviously, manufacturing is hard and testing is hard. But it's also hard in ways that you can't imagine. Like one example is, when people put the device on the windshield in the summers, the windshield gets up to 80 C, 90 C, and then you have your device, and then your device, if your device lags by 4 seconds, I mean, that's 4 seconds later, and then you don't want your AI to act 4 seconds later when you're going at 80 miles an hour speed, right? So that's another reason why hardware is hard and why this is hard. But more from a machine learning point of view, why is this a hard problem, right? So the one big bottleneck to self-driving cars and robotics to some extent is that there is no good world simulator. So why do we need a good world simulator? So let's go back to what happens when you drive a car and when you try to train a model, right? So you drove let's say 100 kilometers, and then you have all this data, and then you want to train a model now. Okay, so you can train the model to take image frames and then output a trajectory. So you have to do a bunch of pre-processing to extract trajectories out, whatever. Let's say all of that is done for you. So now you train a model that sort of takes in the input frames, takes in your car state, and then outputs a command, let's say gas, brake, steering. So this should drive, right? So does anybody sort of have a guess on this? Does not drive. If you train it like this does not drive. Why?
Won't work on new scenarios.
Sorry?
It won't work on new scenarios, anything new.
Yeah, but let's say I drove like 100 kilometers and I just want to run the same 100 kilometers, let's say. I don't want to change much. Yeah, so I have, let's say, like a 10 by 10 grid. I just keep driving in this 10 by 10 grid of like roads, and then I have a lot of data. So I've trained a machine learning model to take image frames or whatever, like a video input, take a bunch of other sensor information, and output the steering or gas brake information, right? And all of my tests look great. Everything looks awesome. My loss go down and everything is awesome. And I put this in my car and my car does not drive.
All sorts of things can go wrong, right? Your perception itself can be broken because you could have things that you are not seeing.
Yeah. So let's downscope the problem. Let's say you won't see anything new. Like everything that you see is things that you've already seen. There are no like different, like whatever. There's no like new things that will come up. Everything is like in distribution.
Okay.
Feedback from the world.
Yeah, that is like the main reason why this doesn't work is because you can train your model to mimic human behavior. It's called behavior cloning, right? And behavior cloning in RL has a very classic issue is that it can run well for 5 seconds maybe, but then what happens is you have errors, like every step has some delta error, and these errors like compound and errors propagate, and there's no forcing function to recover in your model training. So just to rephrase another way is, when, let's say in your model training, right, so you have a trajectory, okay, you engaged, so now your model has to drive. So your model drives, but then it does there is a little bit of difference, right? It moves, let's say it had to move 10 centimeters to the right, but it moved only like 8 centimeters. So now you're in a different world, a world that you don't have training data for, a world that didn't exist because your training data says, it's the next frame is 10 centimeters away, not 8 centimeters away. So now, okay, so what do? You can because you don't have this world. So you don't have the physics of this world, you don't have what happens when you deviate slightly. And then when you roll this out for even 30 seconds or 1 minute, I mean, all the errors add up and your car sort of drifts away and does not recover. And this recovery pressure is like a big reason why just off policy, just doing behavior cloning on these systems that have to just run for a long rollout does not work. So how have other people solved this? Because people do RL, other people have, there are many RL problems like games, and you have agents that do very well in car racing games, right? So why does that work? The reason is that you have a perfect simulator. When you have a car game, you have an absolutely perfect simulator. So what happens, right? I train a model, okay, and now I'm running this trajectory. It made a slight error, but in my simulator, I have this new world. So I have the physics of the world, I have everything in this new world, and then so I have the training data for this new world that sort of came up because my car didn't do exactly what I wanted to. So that is the main reason why this is still a hard problem is that there is no good world simulator. But then the problem gets worse, that you have a very skewed distribution of data. Like all the data that comma has are data of decent driving, right? I mean, nobody flew off a cliff. Nobody sort of got into any crazy accident or anything. All of the data is nice and neat data. So now, how does the model know that driving off a cliff is bad? I mean, the model has no idea what driving off a cliff looks like. So that's why this is an even harder problem than not just having a world simulator. But then there is a compounded third problem, which is that driving is let's say. So what I said till now applies if, let's say, there is nobody else on the street. Let's say it's just physics. You're just working against nature. So you just have to drive on an empty road. That's fine. I mean, all the problems I said apply there. But then there's a third problem of you move 10 centimeters to the right, but then the car to your right didn't like it, and then they sort of moved away, and then somebody else did something else. And this is the counterfactual world information that you do not have. And this is another sort of third layer of reason why this is still a very hard problem, is that you don't have the counterfactual world in which things happen. I mean, if you have a video game, you can program behavior in the video game and you can work around it. But then in the real world, what is like how do I codify this? How do I say to my car that okay, when I did something slightly like sketchy, like the other person didn't like it, and then they did something even sketchier. This is information that it's not in my training data. So, and what is not in your training data is not something that you can work around. This is like another sort of main problem why doing like behavior cloning alone is not sufficient to solve real world like self-driving, but also like generally robotics, real world robotics.
And it's a sim to real transfer problem, right?
Yeah, it's definitely a sim to real task, and there are some problems that are more amenable to sim to real. Like let's say I want to do some grasping action. So you have a laboratory setting, you have an arm that like you can train in simulation to grasp, and then the real world is slightly different, but like it's different. But even in that, if you just put a different like a softer object, like your sim to real breaks now because I mean it didn't learn it. It didn't know what soft objects were. Or if you put like an egg, it'll break the egg. Yeah.
Good question. So that in self-driving, there are different settings of the problem. So yours, is it correct to say that it is a single view, forward-facing camera, no side view as well, no lidar and much lidar or something like that. And so with that now, so the problem setting is, given this single view, can I mean within the limitations of that view, can I drive the car by moving it left and right?
Right.
But probably not do like street driving, I mean maybe like city driving, etc. But at least can I do highway driving? Is that setting correct?
Yeah. But the video that you saw was city driving. I mean, it already drives in cities, and you can already use it for city.
You have other things.
Right. So yeah, this is like a common question. For sure. Yeah, this is like a pretty. I have like a FAQ in the end where this is a pretty common question. Is that so? Is your question that is self-driving like sensor limited or is it intelligence limited? And my claim is that it's 100% intelligence limited and it's not sensor limited. In the sense that like right now these cameras are 360 cameras. It has 180-degree field of view, and there's an inward facing camera that also has 180-degree field of view. So it's like it can see everything a human can see basically. When you're sitting in the car, if you like put your head around, what all you can see, the device can see. So that's like one, and the thing is this thing has more information than you have. It has like very accurate like accelerometer information, very accurate like gyro and very accurate GPS information, which you don't have. But then humans are like really good at driving. So yeah, it's not a problem. It's not a subset of the problem. It's the full driving problem, and it's not like sensor or hardware limited right now. And it's like 100% software limited and 100% like AI limited. Yeah. So to this end.
I have a question. How do companies solve these problems?
Yeah. I mean, it was very creatively. So lidar sort of helps you to some degree, right? Yeah. I mean, you have HD maps and you can do some interesting like. This problem is also relevant when you do fully end-to-end, which is like human-driven trajectory. And I'll tell you, I have some examples why end-to-end and human-driven trajectory is like the answer. Like you can't build a rule-based system that will ever like be reliable, that you can scale to the rest of the world. You may be able to scale it in like a small like setting, right? But an end-to-end system is the only system that works. And for the end-to-end system, I mean, these are some real problems. So some way in which they solve it is, they do have good world simulators. So Tesla has invested like quite a lot in building like a video and hybrid, like sort of a neural video type of simulator. And then even way more, everybody else has simulators. It's like,
and how I mean, the data that you collect, it keeps changing, and the world keeps changing.
Yeah.
I mean, today there's no bridge, tomorrow there's a bridge. Right? So the data set becomes what?
So it depends on what is it that you're getting from the data set, right? So it's not that you have data set of one road and then you have to now drive on this road. Basically, the thing that you distill out of the data set is how to drive, and not like what to do in this specific setting. It's generally like what is driving and how to drive. So an interesting note here is also that drivers may be bad. So drivers are like people are really good drivers. People drive really well. Accident rates are higher than they need to be from technology, but they're not as high. It's not like a crisis. You don't worry about going on the streets. But then drivers are bad in like various different ways. So you have a lot of good training data when you just have people driving around. So I was about to say, so one way in which people solve it which everybody's doing in self-driving and also generally robotics, is to build world simulators. So what world simulators are? So this is Comma's world simulator. So I can just replay it. So basically, the frames that you saw in blue. Okay, I can just go here. So this is the input to the model, and everything that you see in green is simulated. Like the model is predicting what is happening here, and like red is like the future. So this is what was given to the model, and the model is completing it. It's completing the lane change.
So here you're saying there's a 360 view that you're not showing correct.
Yeah. I'm not showing currently. Yeah, this is like a zoomed in like a type of view. But basically, like a world simulator is you train a neural network to take your input state, to take like some history of your input state, some pose, and then you want to be able to predict what the world would look like in the next frame. If you have this, then like all the problems that I mentioned go away, right? Because like, okay, when your model did like some error, like you have information of what happens in the next frame, next whatever second, and then you can train the model to recover. And this is like the holy grail of all robotics companies and all self-driving companies and everyone else. Everyone wants to build a good world simulator. And so I think Comma recently had a paper accepted in CVPR building a world simulator. But this is like exciting work that a bunch of my colleagues have done at Comma.
Is this similar to like the Gaia and things of that sort?
Yeah. Gaia is by Wave. Yeah, it's exactly the same thing. So
that is not, in the sense that's not a full simulator. Like it only is simulator to certain small degree of motion. So you cannot do a lot of a few seconds,
right.
few meters, maybe a few
because
few tens of meters.
Right. I mean, especially because you don't have it in the training data. You don't have it in the data set. But for driving, I mean, that is so. Before this,
that's probably enough.
Before this, what Comma used to do is Comma had this thing called a small offset simulator, which is basically you can take your car, move it. You can take the image, right, and move it slightly, like slightly left and slightly right. And you can, through like very traditional computer vision, change the sort of your perspective, and you can cause like a warp in the image. You can do some very smart things, like you can see faraway objects, and you can make sure that faraway objects don't change. Close up by objects change. You can warp the image a little bit, and then you can simulate as if you're looking from like a different point of view. But that's what they used to do, and all the releases before was with that simulator. But then this is going to be like the game changer simulator, which should have like much more consistent driving behavior, much more human-like driving behavior. This is something I'm super excited about.
How are you generating failure cases? I mean, because failure cases, you have to capture them in the real life for it to predict those images, right?
Yeah.
So like dropping off the cliff, you will not have the data.
Yep.
So how do you generate that?
Yeah, I mean, you can't.
But you collect data from
the same, right? Like
Do you collect data from people as well?
Yeah. This is data 100% from people. This is like, I think Comma has more than like 100 million miles of
mistakes.
Of driving data. So the thing is like, I think we have like the threshold to hit before asking that question is, let's say a reasonable looking road with a reasonable looking traffic situation.
Just to augment your data, so if you have 10 hours of data, you can build 50 hours of data from that 10 hours. Is that what you're trying to achieve with the simulator?
No, but what we're trying to achieve with the simulator is to get the counterfactual world.
If this person was not crossing the road.
Yeah, so I have video of like in this situation doing a lane change to the left, but let's say I couldn't do a lane change and I came back. Like what does that world look like? And that is information that you don't have. That is like that is not in the training data.
How do you measure the quality of world model itself?
Yeah, I mean so this is again like a proper research question. So I mean, one is you chop out a part and then you try to recreate, and then you I mean, it's like a simple loss against what actually happened versus what your model is predicting. That's like a simple way. I mean, they do some very other sophisticated loss on. It's very similar to like like video model that you see, like generative AI video models. This is like a very simple, similar type of architecture.
I'm curious whether you enforce some physics-based loss terms. It's not.
Yeah.
It's just video to simulate and physics at some level of fidelity.
Yeah, for sure. So this is an again open sort of research question, is if you have this data, is physics encoded in it? If you have enough training data, do you need more enforcement, or is it just a model, like model is bad type of problem?
If you have the physics component, you will converge faster, right? Like if PNNs converge faster to certain complex problems than your neural network.
Yeah, no, for sure. And I think physics, I don't think they enforce any physics-based laws, but so one thing is that driving looks very similar, and the physics sort of changes in driving are not that great. I can totally imagine you have to enforce physics when things are like flying out of things and you're dropping things and stuff like that. But that is a much harder problem though, because okay, how do I simulate the physics of what that car did, and now I have to figure out the dynamics of that car, of all the other cars in the thing. What about humans? Like how do I define the physics of these humans? It's like a really hard problem. But yeah, like the current sort of thesis is that if you have enough data, the physics is encoded in this data, and then if you have a model that is really good at it's like the same thing as the Elias take, right? That like a LLM that is giving you an answer to the question is also an LLM that has the internal capacity to think about the world in which this would be the answer, so on and so forth. But yeah, that's the.
Follow-up. Are they actually training models in the world model? Like when you say counterfactual, is it being used? How is it?
Yeah, so the model training is a multi-step process. There is like a simple vision model that just takes frames, gives some outputs. So there is like a model that already knows how to drive. That model is driven in the world model.
Okay.
And that, then you can teach it like recovery pressure. The model will recover, and then they'll get the counterfactual word.
What signal per se? Like, what signal is coming from world model?
So you have the human-driven trajectory, right?
Yeah.
So you have like a video of human driving.
Yeah.
So now I just want to mimic this human driving.
Yeah.
So I have the inputs that the human gave, and then now I want my model to drive like that human. So the issue before was I say this to my model that already knows how to drive, but the model makes mistakes, and now I don't have the counterfactual world. But now I have the counterfactual world. But still, the target is still the trajectory that the human drove. But it's just that I have the new world now, and the model and then that's the reward signal is
it's
to go
like
back.
You're deriving new state.
Yeah, exactly.
Exactly. The targets are the same.
Yeah, the target is the human-driven trajectory, and that's the trajectory that you want to drive on.
So world model is not just outputting video; it's outputting some state information also.
Yeah, I mean the video is just for rendering, but it all happens in latent space.
From latent you're deriving a lot of things.
Yeah. You get
whatever your device would have, you will get from this world model.
Yes, and then your model now continues to drive in that.
The world model is an online environment.
Yes.
Right?
Yes.
Are you using it as in an online setting or an offline setting? Yeah, for training.
Yeah.
But using it as an online?
Yeah, that'd be interesting. You could use it for online also, right? For doing rollouts.
You mean while people are driving? I mean, it's like a tiny box which has, like real world constraints. But yeah, I mean, you can.
No, not that way.
Yeah.
Since you have a world model, you essentially have an environment. So now you can basically get the model to drive in that environment.
That's exactly what is happening. Yeah.
But what are the trajectories? That is an offline data. So the trajectories is offline.
Yeah, but that's the gold data, right? So that's the trajectory that I want the model to drive. But then when I'm driving in the world model, I have the new states. I have you can push the car right to the right, and the car now needs to figure out how to recover back to the human-driven trajectory.
But does this counterfactual actually you encode, or does it just the model drift into some counterfactual?
The model just drifts. It just works.
So it's sort of like a regularization, for lack of a better word, right? Where you're just giving it some differences in what could have happened. I mean, it'd be pretty cool if there is
so I'll tell you how it's
counterfactual,
right.
which is very intentional.
Yeah, exactly. That is, I think, exactly how it's more than just like a regularization, where it's it's actually the world, which is if you have a car, let's say you have a drive where there is traffic, there is your car, and then there is one car slightly to your right? So now if human went straight, but then I'm disturb the model, and then now the model has to recover. So here in the world model, when your car is drifting slightly to the right, the other car would also move a little bit to the right, or would not, and then you have to now recover much faster because otherwise you'll get into an accident. And that is stuff that is only emergent of just having all driving data and just you being able to predict the next state.
So actually, the Gaia one, they actually do something similar to what you're asking. So what they do is they have a language output and a visual output with a joint loss on them. So meaning what I'm doing in my prediction has to match the text as well. And now sort of you can do that in the reverse as well. So you can say what the task you want to do in language, and it will show you that you do that same.
Yeah. Yeah, and so here by language you just have like steering commands. So you can just literally say, okay, I steer to the right.
Yeah, I guess you could train another model to create intentional counterfactuals given a trajectory.
Right.
Like make
but then you
sure
still
it swerves on the right, make sure this pedestrian comes right in the road.
I mean, it's all part of the
model can be generated based on
And for driving, the world model at least is like is pretty limited because your roads generally look the same. But then when you take like robotics or when you take other situations, I mean, it's like a whole other ballgame because like things don't look the same. Everybody's house looks different. And now you need the robot to work not only in your lab, but like everybody's house.
Isn't there any way to make it like fully online? Because you have the reward, right, from the world models, and you can derive rewards like stay on the road, don't kill someone, don't crash into someone.
Right.
So I'm just curious to know why is it being like fully online, and why is that still the trajectory of real offline data as like the gold standard?
No, but what is fully online? Again, like what are the rules?
Online is fully
right. But what are the rules of the road though?
Stay on the road. Like, I'm just curious.
No, I mean, I'm just saying like it's very hard. I'm saying like the behavior of the rules of the road are actually encoded in the human-driven trajectory. Like the human trajectory encodes like rules and behavior of humans, which you lose out if you like. What you're saying is very similar to a GTA game, right? I can train an online thing in a GTA game, but then if you put the same model in like on real world on like Indranagar, I mean that would not work.
It's sort of like internet text and next token prediction, right? Like
right.
That's like a gold label.
Yeah.
Why wouldn't you use it?
Yeah, because that encodes
more data.
But that encodes like all the human behaviors into the thing, which is what you want it to behave like in the real world anyway.
But is the human reaction time also like it's not only about human behavior, right? It's also a function of how sensitivity of your car varies, how much your brake you have to press. It varies from car to car, right? So isn't the calibration, local calibration needed also?
That also is part of the self-driving system. But the major way, like heavy lifting, is done by the model that looks at the video, that looks at the thing and looks at the situation and figures out what is the action to take here. And then this is translated back to like whatever appropriate things are for the car. Like for a big car, you have to like move the steering wheel more. For a small car, you don't.
Training data, like it was a certain situation was there in the training data where a reaction time was due to the good calibration, but in your car, the handbrakes are down, the brakes are heated up, and now you need to react at a different.
Yeah.
Is this an out of distribution data or will it be taken care of?
I mean, it's if you have enough training data, your hope is that not many things are out of distribution. So the situation you're talking about should fully be tackled because like let's say you're on like a slippery road, right? You're driving and your car is drifting a little bit or like this is something that I had to face, which is like heavy wind, like strong winds. So you're driving and then you want to stay in the center of the lane, but then there are strong winds and the winds are pushing you. And this is a situation where the car needs to like put more torque than it would otherwise put to stay in the center of the lane, and that is like you hope that you have 100 million miles of driving data. All of these situations are covered in it.
But does the model get this sense? Like what data does it get from sensors? All the data is this video data, right?
Yeah, I mean it has like
detecting strong winds, for example.
So I mean that's a good question. So how is it detecting strong winds? Is that it knows what it wants to do, which is driving the center of the road. So what is preventing it from driving the center of the road? How to go to the center of the road? Oh, move a little bit to the left, which is what humans do. I mean, you don't get any sensor information.
Change in like the view,
right?
That it will have to. I mean, I don't imagine it's driving like zigzag, right?
Yeah, it's not. Yeah. So I mean, like with strong winds, like literally what happens is you just move to the right a little bit, and then now you're not in the center of the road anymore. So now the model has to figure out, hey, wait, like I had to be in the center of the road, so what is happening?
And then so inefficient, or like data inefficient, to be honest. In the sense that just
I guess humans would do the same.
I know.
In the car,
Exactly my point. I mean, humans are really bad like sensors, right? I mean, you can't sense like gyro. I mean, have you done this experiment where just go with your friend, ask them to go at constant speed, close your eyes, and try to predict the speed? It's like really hard. Humans are really bad at predicting speed.
You can say it's impossible.
Yeah. But I mean, yeah, for sure. But like, even, you have some acceleration cues when you're driving and stuff, but still it's super hard.
We are highly reactive drivers. Right? We are not, unlike the 3D planned system which does very precisely, oh yeah, this is 1 centimeter off and very precisely. We don't do that. We just check, oh, am I there? That's the real principle in some sense.
Yeah, but you want the AI to do exactly.
Of evolution though.
Sorry?
I mean, we had eons of evolution.
Yeah.
When I'm driving, there's a bunch of dust.
Right.
That dust could be paper pieces or it could be nails.
Yeah.
And I know by the reflections of things very quickly that which it is.
Yeah.
And I will
But the model would know this.
Yeah, I mean, 100%. I mean, this is the sort of ultimate question is that are these things, are robotics and self-driving car, are they AGI problems? Like, do you have to have AGI to like really solve this? Or can you say with confidence that, under some circumstances, they're fine. You can and fine to the extent that, you saw the Waymo, right? Which there is no driver. So if, I don't know, if like there was an earthquake, I'm sure that would be out of distribution and it would not do very well. But yeah, that's the hope. Sorry, I think you had a question. Yeah.
How much does emotional intelligence play a role in the system being able to detect and drive akin to a human?
I mean, how much emotional intelligence do all humans have, I guess? I don't know. I mean, it's like...
some people drive in rage,
Right.
some people drive in meditation, some people are listening to a song and they're happily driving.
Yeah, so this is another interesting experiment that Comma did. Basically, with logs, they figured out, they rated all drivers from the craziest drivers to the most calm drivers, and they trained a model on the crazy drivers and on the calm drivers. And there was a mode, there was a chill mode and there was an aggressive mode. And you could toggle the mode, and in the chill mode, you can ask it to go at super fast, and it always goes, in the US, 65 is the speed limit on the highways. You can ask it to go at 65 miles an hour and it won't go above 45. It's chill. And then if you go in the aggressive mode, if somebody's there, it goes right behind them and then brakes really, really at the end. Yeah, I mean, these behaviors are encoded in the training data and encoded in the model. Yeah, so.
And follow up on that, do you want to then, since if you have the data, standardize the mode that you're supposed to go chill mode no matter what?
I mean,
your machine and really not having a bad day, unlike a human at work.
Yeah, sure. I mean, you definitely want to avoid crazy drivers and you want to exclude that data out. But I don't know, I'm very hesitant to say things like you're supposed to do this. I mean, let the model do whatever it wants to do. I mean, it's fine. It'll take you to your destination. And it'll do whatever is appropriate. I mean,
it uses the option, right?
Yeah, users the option is one. And the other thing is, one of the things that comes up in self-driving cars is if everybody, it's like a game theoretic thing, right? If everybody knows you're the most, you're the calmest, or you will never do aggressive things, then everybody will take advantage of you on the road. So I guess it's important for everybody to know to not take advantage of a self-driving car.
And then, actually happened to Cruise and Waymo in San Francisco, right?
Yeah, but Waymos are super aggressive now. I mean, right now they are really cool. Yeah.
Yeah, lots of questions. Yeah, maybe you can ask us that later.
Yeah, I'm just a couple of things. I mean, I just skip over a couple of interesting projects I worked on. I'll just talk about the last one a little bit, which was model introspection. So this is a cool test that we had for the model, which was, so we want the model to go straight, right? But then, we realized in some situations that, if the model is slightly off, it's not going straight, it's just continuing to go. And then if you look at human driving data, it's how often do you, when you're going slightly away, do you come back to the center versus you just keep going straight? So this was a cool test where we started so this is the center, and these are different offsets. I think it's a few centimeters to a few meters. We offset the car and then drive and then let it go and then ask it to do whatever it wants to do, and then it wants to come back to the center. And this was a pretty cool test to figure out how well the model has been is behaving. And another interesting tidbit from this is when we split this on which lane you are you on the leftmost lane versus rightmost lane? And there was a very interesting difference is that if you are on this middle lane, it tends to be more in the center of the road. But if you're on one side, because it knows there's no other car on that side, it tends to be slightly more lax, which is a pretty cool emergent behavior out of driving.
How did you decide that this needs to be solved?
Yeah, I mean, people complain. I mean, the thing with Comma is, everybody at Comma drives a Comma. So, you're going on the highway and it's not in the center, and you're like, why not? And then that was the motivation to fix it. Yeah, so I showed you this screenshot from before, and I showed you there is a comma logo there, which is another car. So how comma doesn't make cars. So comma makes these things called comma bodies, which sort of register as a car. It's just a hoverboard with a stick, and the same device sort of you can put as a face, and it registers as another car, and the same model drives. We have tried it. We've just put it on the street. I mean, this is inside an office. You can see it drive around and try to chase this person. We also just took it.
So.
Yeah, I mean, it drives wherever there is a path to drive.
It's very drivable because of the lane cruise thing that you're using with the other cars, right? Because if you are doing like a road-based thing, then pretty much hard for you to drive on this with same
I mean, like as I showed you, right? Like in the tree farm example.
Yeah.
I mean, it just drives. It just drives wherever. Like if it thinks this is a drivable area, I mean, it drives. But yeah, that was like a cool company side project. That was. Yeah, okay, so this is like the last bit, and then we can go to more questions. So there are some cool data sets from Comma that you can download and you can try stuff. There are like 3 data sets that I've highlighted here. So that one is called Comma 10K, which is, I think, the largest and the best segmentation data set. So that, interestingly, was segmented entirely by like contributors. It was like a GitHub project with 10K images, and people just self-organized and like segmented, and we have ground truths, and that is incredible because I think we went to like one of these model data providers and they asked for like a shitload of money, and then we put it on GitHub and then people just did it, which is great. So you can train segmentation models, you can do cool stuff with that. The second thing we have is it's called the controls challenge. Basically, you can't see the axis here, but it's basically how much you're instructing the car to turn and how much is it actually, like how much torque you're instructing the car to do and how much lateral acceleration you actually get out of it. So this depends on the car model. So car models have some internal physics and internal like, I don't know, internal like equations basically that convert the instruction you give to like the weight of the car and then the velocity of the car and everything to actually perform, to actually turn the wheel physically. So we have a really interesting, this is like the largest data set accumulated like this by ever because Comma is the only person who has this information. So this is an interesting data set to just play around with. The third interesting data set is the compression challenge data set. So this is all, you can see the flicker, this is an imagined video. So there is 100,000 minutes of driving video on the Comma VQ link. You can just go download all the video and you can try to build a world simulator. So that's something that you can play around and do. Okay, so question time. I've just preloaded some questions. So will this ever work in India? So, I mean, yes, it will. And the reason is because you drive in India, and if you drive, like, unless there's a strong reason why, like AI is, for some one axis, can never achieve that humans have, there is no reason why it won't drive. And if you can see, there is, so that is the image of training data distribution for the last run from Comma, and you can see there's like a tiny dot in India right there. So India is in the training set, which is great. What do you have? US is mostly in the training set. So this is like a data problem and a algorithmic improvement problem, but it will drive in India. Yeah, the second question is, I guess, can you just use one device? Don't you need LiDARs? And you don't need LiDARs. It'll just work because, again, as I said, you don't have LiDARs and you drive just fine. So there's no reason why it needs LiDARs. Can you just do with one device? I mean, you can put another device at the back. Again, as I said, it's mostly a software problem right now because all the errors that Comma makes, we used to have TVs with just errors, and you go look at any error, none of that is like a hardware sensor error. It's all because like, the models are dumb. And then when the models are less dumb, they will like pass those situations. I guess the last question I get a lot, and I used to get when I used to work was, Waymo, Tesla, Cruise will do this. Comma is like 20 odd people, by the way. What can 20 people with like 1/100th of the funding even do? I mean, this is like a more philosophical thing, I guess, which is, I mean, you want that car to be self-driving, right? I mean, like a Waymo car you see is like a massive 300K car that you will never own. But what you can do with Comma is you can download an AI, put it in your car, go to a tree farm, cut off from the internet, and it's just you, your car, and the tree farm, and just keep driving. And that's the dream, and that's like awesome. So yeah, that's it. That's my talks.